Hello again. In this video, we'll do some more problems on the scientific method just to make sure that you understand the concepts and you are able to appreciate that the same concepts can be used in various problems. So it's but before I do these additional problems here on Ohm's law and electrostatics, so I think I have electrostatics here as well, somewhere here, but I've included these ones just to highlight that the same principles will apply the same principles on all of these problems. May I ask you to actually take a look at this question. You can pause the video at this moment and then attempt this question. Question is still on EMF. So you can attempt this question and then you can view. I'll do the solutions right at the end of this video. So you have learners perform an experiment to determine the EMF and the internal resistance. And then you have this circuit diagram here with the variable resistor R, and then there's a switch S, and then this is the ammeter, and then this is the battery with the EMF and the internal resistance. So learners use their recorded readings of current and resistance together with the equation R is equal to E over I minus R. I'm sure that you can write this in the form of Y is equal to mx plus C. And then you answer these questions: which variable must be kept constant during the experiment? And then I'm going to refer to the graph. And then this is a write down the value of the internal resistance of the cell. I think by looking at this equation, so when you write it in the form of Y is equal to mx plus C, and noting what's on the y-axis is resistance, what's on the x-axis is 1 over current, then this should be trivial. And then you calculate the EMF of the battery. You'll use the same methods in the previous video. Of course, you must understand that what each variable represent in this equation, in the sense of which one is x and your y and your c, and then you'll be able to answer all of these questions. Okay, so now let's let me do these few more questions here. This one is on Ohm's law, and the content here is on the video scientific method experiment results, where I explain ohmic and non-ohmic conductors. Okay, so 9.1.1, we should state Ohm's law in words. And 9.1.2, which one of the following two conductors, X, Y, is ohmic? You refer to the graph to give your answer. Okay. So let's do this question and then let's do the rest here. So 9.1, the two graphs below show the relationship between current and potential difference for two different conductors, X and Y. The graphs of I versus V for two different conductors, X and Y, is given below. This one is the current in the y-axis in milliamps, and this is your potential difference in the units of V. Now 9.1.1, we must state Ohm's law, so let's do that here. 9.1.1, what is Ohm's law? Ohm's law states that the current is directly proportional. Current is directly proportional to voltage, and is inversely proportional. So the current is directly proportional to voltage and is inversely proportional to resistance. Okay. Then on the condition that provided the temperature is kept constant, so we don't vary temperature. Okay, so at constant temperature, then current is directly proportional to voltage and is inversely proportional to current. Which one of the two conductors, X or Y, is ohmic? And then you can refer to the graphs. You can see that for graph X, for the graph of conductor X, we have a straight line which shows that the relationship between current and potential difference is linear. And for conductor Y, we have a curve. So the potential difference as potential difference increases, the current also increases for both conductors. But for conductor Y, the graph is a curve, so it's not a straight line. So this is not a linear relationship, and therefore this is non-ohmic. Conductor Y is non-ohmic, and for conductor X, it's a linear relationship that says that it means that current is directly proportional to voltage. Okay, so the conductor that satisfies what's described in 9.1.1 is conductor Y. So 9.1.2 so the conductor X is the one that satisfies the definition in 9.1.1. Conductor X, the graph of I versus V is a straight line. Okay, or you can say that I versus V is linear. So since this graph is a straight line, it indicates that indicating current is directly proportional to voltage. Okay, but for conductor Y, it's non-linear. Okay, so conductor Y is non-ohmic and conductor X is ohmic. All right, so that's it for this question. And then let's take a look at another question. Again, we will use the scientific method as well here. So learners investigated the relationship between potential difference V and current for combination of two resistors R1 and R2. In one experiment, resistors R1 and R2 were connected in parallel. In a second experiment, resistors R1 and R2 were connected in series. The learners plotted graph X, results of one experiment, and graph Y, results of another experiment as shown below. So this is the graph of potential difference versus current. On the y-axis, we have potential difference with the units volts. And on the x-axis, we have current with units amperes. And then this is a graph of x. And then this is a graph y. And you can see both of these graphs are straight lines. So then we expect that both of them obey Ohm's law. Right? And then 9.1.1 we've already answered in the previous question. Ohm's law, current is directly proportional to voltage and is inversely proportional to resistance at constant temperature. Okay, so let's just answer 9.1.2. Select the pen here. 9.1.2 just erase that. Right, the what physical quantity does the gradient, which is the slope of the graph vi, represent? So to answer this question of what physical quantity does particular graph represent, does the gradient of that particular graph represent, then you answer this question by saying that the gradient is the change of a variable in the y-axis, which is in this case is potential difference, divided by the change of the variable in the x-axis, which is in this case is current. And then you look at this equation of quantity divided by which quantity represent what quantity. So in this case, the quantity V divided by the quantity I represent resistance. So for 9.1.2, the gradient represents resistance R. Right, and then 9.1.3, calculate the slope of the graph X. So you just select any 2 points to calculate the slope of graph X. In this case, I'm going to select the origin and any other point, which is I'm going to select 2 and 0,5. So then the gradient again is going to be change of the variable in the y-axis divided by the change of variable in the x-axis. Then I'm going to select 2.00 minus the origin is 0 divided by, when the voltage is 2, the current is 0.5 minus 0. When the voltage is 0, the current is also 0. And then what do I get? I get 2 over 0.5, which gives me 4. And from 9.1.2, we've stated that this gradient represents resistance. So therefore, this is 4 ohms. Right. So we determine the resistance R1. So now, how do we determine resistance R1? We must first note that these graphs X and graph Y, they are potential difference across this combination of resistance, and this Y is, we don't know what the combination, whether it's series or parallel. It is not stated here. So we need to figure out first which one is series and which one is parallel. And we have 2 unknowns. So then we will have simultaneous equations to determine resistor R1. Okay, so let's first figure out which one is series and which one is parallel. So we'll proceed as follows. We should 9.1.4, if you do analysis, then you know that RT X is R1 plus R2. Sorry, you don't know whether this is series or parallel. Sorry. So we're just going to say that RT series is R1 plus R2. So that's a series combination. Okay. And then RT for Y, total resistance for the parallel combination is it's that there. So this will be the parallel combination here. And what we know about this parallel series relationship is that the resistance for a series combination is bigger than the total resistance of the parallel combination. Okay, so that's what we know, is that the knowledge we have from the theory is that this total resistance of the series combination is bigger than the total resistance of the parallel combination. So then that means then we just have to look at this graphs here, because we already have information about resistance, which is the gradient. When we look at these two gradients here, we can see that what is the gradient of the graph y? Well, if I go on the x-axis, if I go 0.5 units, and then what is my change in y? So if I go here, that's change in 0.5, and then this also change in y is the same, which is 0.5. So the change in x and the change in y are the what? Are same. So therefore the gradient of the y graph is 1. So then we deduce that since the gradient of the graph is 1, we deduce that the gradient, so RTX, total resistance in x is greater than the total resistance in the what of y. So then RTX is a series combination. So RTX is a series combination because total resistance is bigger than the y, and therefore RTY is a parallel combination. So then the total resistance is given by these equations here. Okay, so again we just looked at the total resistance of the graph x, and then we note that since the gradient here is 4, the gradient is 4, and the gradient here is 1. Since the gradient represents resistance, so we deduce that this resistance of this combination is bigger than that. So this must be a series combination, and y must be a parallel combination. Okay, so then we proceed now with this our simultaneous equation. So we have R1 plus R2 is equivalent to 4 ohms, and then we have R1 R2 over R1 plus R2, which is equal to 1 ohm. Okay, so this is our simultaneous equation. Then what we can do, we can form equation 3 by saying that R2 from equation 1, R2 is equal to 4 minus R1. I'm going to drop the units. So this implies then that if I substitute, so I have R1 into 4 minus R1 there is equal to, so I'm going to substitute, maybe let me not, we just substitute first, R1 plus 4 minus R1 is equal to 1. So that means that 4R1 minus R1 squared is equal to, so R1 and R1 they cancel out here. I have 4, so I'm going to put this 4 here. Okay, so then that means that R1 squared, so this, I'm going to take this to the right hand side, and then we're going to leave everything on the other side 0. So then that I'm going to get minus 4R1 plus 4 is equal to 0. And then R1 minus 2 whole squared is 0, which implies that R1 is equal to 2 ohms. Okay, and also R2 is also which is 4 minus 2, that's also 2 ohms as well, right? So that is that's how we answer 9.1.4. okay, right? Now let's look at question 8 here. So we have a circuit, and then we have the voltmeter across a variable resistor there, and we have a battery, and then what we're given is a graph of power versus 1 over resistance, P versus 1 over R, and we are asked to use this graph to calculate the potential difference across the resistor, right? So how do we do that? So what we are asked to calculate is the potential difference, and the information contains power and resistance. So then the first step is to establish the equation that relates the three variables. So the equation that relates the three variables is power is v squared over r. So that is the the equation that relates power, voltage, and resistance. And then we linearize this. So then, because we asked you to use this graph, so then we will linearize this. Power is equal to v squared into 1 over r. And now it's in the form y is equal to mx plus c, where our c in this case is 0, with y is p, and the gradient is v squared, and our x is 1 over r, which is in the graph here. So then what we need to do is that since we have we know that the information about potential difference is given by the gradient of this graph, power versus 1 over resistance. So then we proceed by calculating the gradient of this graph, which is the change of variable in the y-axis divided by the change of variable in the x-axis. So then you can select any points. Since this starts from the origin, I will select the origin and any other point here. I'm just going to select 202. So the gradient of this graph is v squared. So we'll write that as v squared. So the gradient is v squared, and then here I will choose 200 and the origin 0, and when the power is 200, 1 over r is 2, and when the power is 0, 1 over r is also 0. So that implies then that v squared is equivalent to 100, and therefore V is equal to 10 volts. Okay, so it is as easy as that. All right, so let's move on to the next two questions. Okay, so let's look at this question. What do they want here? The relationship between electrostatic force and charge is illustrated in the graph given below. During the experiment, the second charge and distance between the two charges are kept constant. So we have the electrostatic force on a particular charge due to some other charge that doesn't change at a particular distance, which is also kept constant. So then we change the charges here, and then we measure the electrostatic force. So this is 1 microcoulomb, and then here that's 2 microcoulomb, 3 microcoulombs, 4 microcoulombs, 5, 6, and so on. And then we measure the electrostatic force due to some other charge there. Okay. So now we can see that the relationship between the force and the charge is a linear relationship. And so then we are able to answer immediately 8.4.1. What is the mathematical relationship between electrostatic force and the charge, so that you can deduce? So it's the relationship is a linear relationship. So we can say that the electrostatic force is directly proportional. So that's what you can deduce, directly proportional. Now to what? To charge. So that's what you can deduce from this graph here, or that the relationship is a linear relationship. Okay, so that's what we can deduce. Since it's a straight line, we deduce that the mathematical relationship is directly proportional. So 8.4.2 is asking us to calculate the magnitude of the electric field when the charge is experiencing a force of 0.005 newtons. And this is where when the force is 0.005 newtons, the charge that we have there is 1 microcoulomb. Then we want the electric field. So the formula force charge electric field is force per unit charge. So this is what we want here. Then what do we get is that the force is 0.005 divided by the charge is 1. That's 1 microcoulomb. Minus 6 there. Then what do we have? We have 1, 2, 3. So that's going to be 5,000 newtons per watt per coulomb. Okay. And then we look at this question here. That's question 7.2. Again, we're going to apply the scientific method here, lessons, the concept from the scientific method lessons to answer this question. Okay, so let's look at this last question. All right. Let's look at this one. All right. P is a variable point in an electric field of a charged sphere A, and R is the distance between point and the center of sphere A as shown in this diagram. So a learner determines the magnitude of the electric field at point P for different values of R. Sphere A is then replaced by another sphere B of a different charge. And then another set of results are obtained. Now we have these graphs here. These graphs are obtained from results for sphere A and sphere B. And then you have the EA is the magnitude of the electric field at the distance 0.04 meters from the center of the charged sphere A. Use these use the graphs to determine the following questions. So must use these two graphs, sphere A and sphere B. So these are the graphs of the electric field versus 1 over r squared. Okay, so 7.2.1 is asking us to state the proportionality. I think between E and 1 over r, so it's easy, 1 over r squared, and we just look at the graph and you see that we see a straight line graph. So E is directly, so it's a direct relationship. It's directly proportional to 1 over r squared, because we're getting a linear relationship between E and 1 over r squared. And then 7.2.2, calculate EA. So we want to calculate this Y value here. If you are given this X value and you're given the gradient is 680, so 7.2.2, we will have to first write the equation that relates all of these, electric field and distance. The equation is KQ over r squared, and then we must write it in the form y is equal to mx plus c. So this is our y, and then KQ is our gradient, and then our x is 1 over r squared. So y is E, m is equal to KQ and x is 1 over r squared. So we're given x, and in this question we're given the magnitude of the gradient, that kq is equal to 680. So therefore we want EA. So from this equation we'll substitute in the place of kq, which is our gradient, 680, and we are given 1 over r squared is 104 squared there. Okay, and let's take our calculator and see what this gives us. So we'll have 680, right, divide by 0.04. I don't know how to use this. 0.04. So do it this way. And then what do we get? 45,000. Okay. Let's put that here. And then what do we get? We get that our EA 45, 3 zeros, newtons per watt. This is electric field, so it's newtons per coulomb. Okay, so so our EA is 425,000. That's the answer for 7.2.2. Then 7.2.3, how does the magnitude of the charge sphere B compare to the magnitude of the charge sphere A? And you must choose greater than, smaller than, or equal to, and then you have to give a reason for your answer. Well then, here again we'll use this linearization, and you note that the gradient for both graphs, the gradient is kq. So therefore the gradient of this sphere, of this graph of sphere A, electric field versus distance for sphere A, is kqa, and the gradient here is kqb. So that's how we're going to answer this question, by noting that the gradient of this graph is bigger than the gradient of this graph here. So then that means qb is bigger than qa, since k is a positive number. So that is 7.2.3. So that's 7.2.3. From the graph we note that the gradient for charge B is greater than the gradient for charge A, or we can say that kqb, kqb, so this implies kqb is greater than kqa. So let's see. Right, so since the gradient of the graph of sphere B, since this gradient means that kqb is bigger than kqa, then we deduce that charge B is greater than charge A. Okay, that is magnitude of charge B is greater than charge A. Okay, all right, so that is how we answer this question, 7.2.3. And now let me go and answer the activity that I gave you in the beginning of this video. So in order to answer this question, we must look at the divisions. So the division goes as follows. On the y-axis, we have 0, and then we have 5, and then we have 10 and 15. So then since this is 5, so we need to determine what scale has been used for each division line. So if we use we take this as 0.5, then that is 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5. So that's how this division works. Let's look at the scale on the horizontal lines, on the vertical lines, sorry. So we have from 0, this is 0.5. Then each division here is 0.05. So this is 0.05. And then this is 0.1, 0.15, and then 0.2, 0.25, 0.3, 0.35, 0.4, 0.45, and 0.5. Okay, so that is how this division works. So now let's answer the questions. So I'm going to start with 9.1. So in order for this to be kept, the variable that you need to keep constant here is the EMF. So you make sure that this, for us to have this straight line here, we need to have the EMF, of course, the internal resistance. So the EMF, the variable that must be kept constant during the experiment is EMF, and also the internal resistance, or let's just say the battery itself. So it must be kept constant. And then 9.2, so refer to the graph to write down the internal resistance value. So in order for us to answer this, we must linearize the equation first. So R is equal to E over I minus R. So then R, which is our Y, is E into 1 over I minus R. Then we can see that our Y is equal to R. The gradient is equal to E, and X is equal to 1 over I, and C is minus R there. So we need to look at the intercept. What is the intercept? So let's look at the y-intercept to determine our internal resistance value. So let's do that. Then we have 0.5, and then we have 1, 1.5, 2, 2.5, 3. So we have minus 3. So the internal resistance, so for 9.2.1, so this is 9.2.1. So the minus R is minus 3. So our internal resistance is 3 ohms. Okay. And then 9.2.2 is asking us to calculate the EMF of the battery. We've already linearized the equation. So then all we have to do for R versus 1 over I, we calculate the gradient of this line here. Okay, so let's go on and calculate the gradient of the line. 9.2.2, right? So the gradient, change of the variable in the y-axis, divided by the change of variable in the x-axis. Okay. So then, and then we can select any points that we want. I'm going to select 2 and 10.5, 11. So that's 2 and 11. So our EMF is going to be so we have a 11 minus and then you can select any other point. So let's see. Okay, so go to select this one here, this point. So that's 5.56, 6.57, 7.5 at 1.5. So let's do 7.5. So that's 11 minus 7.5. So that's 7.5 divided by, when our R is 11, we have 2. So this is 2 minus 1.5. So we will get 2 minus 1.5. And then what does that give us? So that should give us 3.5 divided by 0.5. So then that gives us 7 volts. So that is our EMF. Okay. All right. Thank you for listening, and I hope that you learned a lot from this tutorial. See you in the next video. Bye for now.